fascinating topic to me. I'm involved with quantum computing, not quite the top dog, but one of the dogs running around in IBM research and in exploring this. And we've touched on so many different things this morning related to applying technology. And that's pretty much why we're all in the room. And I hope to be able to give you some ideas and insights as to how quantum is going to help us with that. So as we think about applying technology to solve problems, that's what we're talking about all day today, right? Is trying to figure out how to apply technology to solve our business problems. Every company needs to make money, save money, or mitigate risk, and we're trying to figure that out as a team, as we gather here and explore that. So I am in IBM research. I live in Chicago, but I work out of the Yorktown Heights Research Center, which is north of Manhattan. So let's get into this wild, crazy, often misquoted idea of quantum computing, and then I'd love to leave some time for some questions. Lastly, also, we just had our CISOs, or some of our chief information security officers up here, and we're going to talk a little bit about what we refer to as quantum safe, which is protecting against the threat of quantum, and I'm going to touch on that at all. Is this giving you feedback? Is it a fair amount? It's good? Okay, all right. All right, so let's keep going. What I want to start with is we're going to go with low tech first, and you may have to wipe your hands off for this because you'll need all 10 fingers for this, maybe all 10. I want you to give me an idea of where you're at on your quantum journey. What do you know about quantum computing? So from 0, which is maybe you thought it was spelled with a K, that's all right, quantum, all the way up to 10, which is what I call the triple Ps. Those are people that I'm surrounded by they have PhDs in quantum physics or quantum computing. They've written papers, they have patents. So triple Ps is a 10. Maybe a 4 or a 5 is you've read some books about it, you had some physics background or quantum physics background, you've watched some YouTubes or something. So just a show of hands in the room here of 0 to 10, where are you at in your quantum computing understanding? All right, I just ran a quick algorithm and we're at 3.79 here in the room. 3.795 actually, got it, okay, yeah. So we're all at different stages. I actually hope to shift you a little right today, maybe not quite to a 10, but shift you a little bit right today as we explore this topic together. And so that you leave with some insights and ideas. Because it's really all about how do we apply this technology? How do we go solve a problem? How do we make better bourbon? How do we provide better healthcare with quantum and quantum capabilities? So that's hopefully maybe you'll spark some ideas. And we often say that this stage of quantum computing is absolutely an invitation to innovation, because we can think differently and solve problems differently. So that's what we'll dive into. I'm going to talk about kind of what is it first. We'll start there. We'll move through a little bit of a quantum computing overview. I am not a quantum physicist. Anybody studied physics? Anybody studied physics here in the room? Okay, any quantum physics? Okay, any quantum physics at all? Phew, okay, good. That's fabulous. So I can just make stuff up on the way. So then we'll talk a little bit about, I won't make stuff up on the way. We'll talk a little bit about IBM Quantum. We are currently leading today, and I can substantiate that. That's not just me saying that, and we can kind of substantiate that IBM is leading in this space, and there's a number of metrics we could talk about. And then we'll talk just a little bit, just a touch on how do we apply this, who's applying it. I'll give you an example of that just from the start. We'll get into more details. Yesterday, is anybody familiar with Cornell's source for publication called the Archive? A-R-I-X, the Archive? One or two in the room. That's typical. Unless you're embedded in research, you typically don't know what the archive is. But that's where all these technical publications are posted. So you can learn a lot by going to the Archive, A-R-I-X, the Archive, and you'll see all these very, very deep papers on quantum computing and apply differently. Yesterday, one of my customers that we can talk about today, Vanguard Financial, one of the biggest financial companies on the planet, and many of you may invest with them or have access to them. They just published a paper on how they're working with us to do portfolio construction and portfolio optimization. So that's an example of how it's being used and explored today. Not yet in production. Nothing is in production with quantum computing yet. So, and we'll talk about that. I'll talk a little bit more about that. So, but we'll get to that so you can start to get some ideas. So why do we need quantum? And that's really a good starting point. This happens to be just one of the largest supercomputers, now we call classical computers, largest supercomputers on the planet, not too far from here, Oak Ridge National Labs. And it's measured in the gigawatts of, compute power. I mean, it's just massive compute power. So why do we need quantum if we have incredible supercomputers like this one? Well, the reason is we can solve a ton of problems. All of you are in the room here because you've done that. You've solved problems with classical computing. There's a lot of problems that we can solve, but we can't solve all of them. Quantum is going to be solving problems that cannot be solved today with classical computers. And we'll talk about why and what's different about it and why it's a completely different type of compute. And so we'll try to highlight some of those. But we will always, classical is not going away. We are not replacing classical with quantum. We're going to augment it. And in fact, this integration of classical and quantum will stay for what we think basically forever, is figuring out how to do that classical and quantum and combining those, the powers of both of those. I'd love for you to leave the room and tell all your friends that you got exposed today to a different type of computing. It's the first time we've really had a branch, a new type of computing since basically computing, whether it was mechanical long time ago, up till today, we have never had a different type of computing. Quantum is a different type of computing. Why? What's similar about every computer on that blue dot before we get to quantum computing? Anybody know what's similar for a $100,000 Amazon gift card? Anybody know what's the same? What's similar about every computer we've ever used? Yes, I heard it from many people, so we'll just spread that Amazon. I know, yeah, I'm gonna be really busy afterwards, yeah. They're based, every computer we've ever used has been based on bits, zeros and ones. Think a light switch, right? Now, amazing things can be done with that, and we know. NVIDIA came up a minute ago, I think, from Aaron talking about going to the NVIDIA conference, but incredible technology, incredible capability on chips today. We actually, in IBM Research, actually design chips, new chips. We don't fabricate them, but we build them. We're doing them for actually inferencing these big LLMs, large language models. So not the compute power needed necessarily to build the LLM, but a really, really fast chip to inference. The one when we go to ChatGPT and say something, we use something different, but and inferencing it. So lots of incredible things can be done with bits. I'm gonna contrast that with what a qubit is. A quantum bit, okay? All right, so what problems will we solve above and beyond what classical can do today? There's really three categories. One is simulating nature. Cleveland Clinic is the first entity to actually buy a physical quantum computer from us and put it outside the walls of IBM. Most everybody here for years and years and years is simply gonna access it in the cloud. They're not gonna buy a quantum computer. But Cleveland did. There's 8 people, 8 groups, organizations that have bought them directly from us. They're expensive. They're over $100 million. So they're not inexpensive. If you'd like one today, we have a special out back. But so simulating nature, Cleveland Clinic using it to simulate nature and develop new drugs. Super promising area of research. Simulating nature also relates to material design. We'll talk about Boeing in just a second. There's a slice of AI that we'll be using and leveraging QML, quantum machine learning. And so there's another category that will be solved. And if your AI problem is this big, probably this much of it will be solved with quantum. It's thin slice over here for fraud detection, anomaly detection, those types of things that does it in different ways than classical does. And so you'll see that integration of the AI problem, some of it will be solved with quantum in the future. And then the other one, a huge one, probably the one that's gonna be the most dominant one initially is, well, between simulating nature and optimization, but optimization. So that portfolio optimization, I just gave you an example of Vanguard Financial, that's public now information. We'll talk about some others. So not replacing classical, different than classical, will solve different types of problems. These are some of the areas that are being explored. I don't expect you to absorb all this. It's just a quick glance at some of the problems that are being solved right now, and people are exploring these types of problems, from fluid dynamics, process planning, and I'll give you a couple examples of these at the end and we can talk a bit more about it. But I just want to focus on one. It happens to be my account, Boeing. And they're using, they have a quantum program that they've been doing quantum and exploring it for about 5+ years now. Very, very key to that, to aerospace, to manufacturers. But they're doing surface corrosion analysis. And when you talk to them, they'll talk about two primary things that they're doing. They're studying what happens at an atomic level with water when water corrodes magnesium. Super important for wing structures and other fabrication in the aerospace industry. So they're literally being able to simulate that on a computer. That really can't be done easily unless you have a mega supercomputer today. So there's promise in that arena. And also studying material development, material science, material fabrication. And so design and fabrication to build new materials will be done by simulating what happens there on a quantum computer. So just one example of Boeing just jumping in. But this is where we talked about this invitation to innovation. There's going to be many, many, many things that will be developed using a quantum computer that we don't even know about yet. That's why we work with clients quite closely at these early stages to try to think together on these problems. And we'll be in rooms and we'll be talking about a route optimization problem for Hyundai. I'll talk about that later, some work that they're doing. And they'll apply that to UPS. We talked about UPS earlier, we had flight, poor Sam got stuck on a plane for a long time, flight optimization, or even the whole airline optimized. So things like that require incredible compute power in a kind of a different way. So one thing to ponder is, what are the problems that you can't solve now because you don't think a computer can solve them? That might be on the list of what quantum can do. And as we'll explore this together. So again, I'm not a quantum physicist. Most of my background is in business, but I just love my job right now, being embedded in IBM research, working in quantum. It's super fascinating. So what is a quantum computer? Does anybody have a working definition? It's just a working definition or idea. How would you describe it? Go ahead.
Quantum computing leverages quantum mechanics to provide multiple state analysis with more than one quantum be able to leverage the quantum properties of atoms to fuzzy definitions.
Good job. Bravo, what's your background?
Electrical engineering originally. I just read PQ
Okay, fantastic. Yeah, I've got it. All right. Well, welcome to quantum physics now. Entirely different, and yet built on some of the same principles. Very, very good kind of direction on quantum computing. Others? Anybody else want to give it a try? All right, we're going to go with that one. It's pretty close to how I would describe it. It doesn't necessarily describe it yet, but it basically points to that we're going to leverage quantum physics or quantum mechanics. We'll kind of use those interchangeably to do compute, and that's never been done before. And to try to differentiate that bit and qubit, this is not a perfect explanation. So if you've got a deep physics background, you won't agree with this completely. It's not entirely precisely correct, but it gives us a little bit of somehow being able to paint a picture in our mind of how a bit and a qubit are different. I'm going to describe a couple of the principles here in a minute. A bit, lots of bits next to each other, makes up all the computers we use today, everyone we've used. And think light switch, right? Just on or off, 0 or 1. And lots of them together can do really incredible things, 0 and 1, but a light switch. Think of a qubit, a quantum bit, the fundamental building block of a quantum computer can be a dimmer switch that can also change color. Now, if that's the building block of the computer, and I can be in all those positions, I've got a lot more compute power, and I can do a lot of things that I cannot do with classical. Okay, so that's not perfect. My scientist friends yell at me when I use this, but it does resonate a little bit. And remember, if you reflect back to Einstein, he kind of argued with, no, this isn't really a thing, quantum physics initially. Because it was at the time in the late 20s, it was counterintuitive to the physics that they were studying, and so just kind of interesting. So let me talk about 3 different kind of areas that we leverage for compute. One is called superposition. I kind of just described that, where a qubit can be in this linear combination of 0 and 1. It's not it's not exactly correct to say it can be 0 or 1 at the same time. It's actually a linear combination of 0 and 1. But again, if you picture this block sphere, if you picture a golf ball, perfect for today, and we can be at any divot on that golf ball. Again, not a perfect scientific explanation, but at least starts to paint a picture in our mind, as opposed to just the top, the North Pole and the South Pole, only those two positions. It can be a dimple on the golf ball, if we go with that example. So superposition. The second one is what Einstein referred to as spooky action at a distance. If you've ever heard that term before, it's about entanglement. And it's this perfectly correlated, two qubits can be perfectly correlated. And if they are perfectly correlated, you can leverage that for compute. Because if I know the state of this one, I will know the state of this one, and I can use that for compute, okay? Again, this is not a quantum physics lunch lesson, but it's just to give you a snapshot of what we're doing. And then interference is a little bit easier to understand. Think noise-canceling headphones, right? I mean, I want to amplify the right signal, and I want to decrease the wrong signal, so to speak. So those three things are some of the quantum mechanics principles that we use. And Feynman, if anybody recognizes this is Richard Feynman. I'm getting one head nod in the back. One of the brightest people, literally, who's ever lived, and specifically in quantum physics. And this is what he says. I can safely say that nobody understands quantum mechanics, okay? So, and every time I ask my PhD friends to describe something, they'll tell me, because they know me now, Duane, you won't get the math. And I have an econ degree, I have an MBA, I've got a master's in organizational behavior, I've got some other stuff that I've studied, but like, if you don't understand the deep math behind this, it's really hard to do the translation. So, and I love Richard Feynman's quote. I'm trying to get through some of his materials now just to understand it myself even more. Question for us, lunchtime question. Before I pose this question, how many quantum computers are on the planet today? How many classical computers do you think are on the planet today? Laptop and above. How many would you guess? I think I heard billions, and the answer is billions. It's somewhere 5 billion-ish. I mean, it's an arguable number, but that gives you a magnitude, order of magnitude. Let's just go with 5 billion laptops and above. Does not include our smartwatches, our phones, everything else. How many quantum computers do you think are on the planet, fully quantum computers on the planet today? 40? 2? 10? 0. No. There are about, we don't, I can be accurate, we don't know. But we think we know, there's about 250. And we don't know exactly how many China has. That's probably the biggest variable. We've built 80 quantum computers, IBM has. So that's one of the things I can point to that I can say we're winning. We're leading right now. Doesn't mean we'll always lead, but we are definitely leading right now. Not all of them are in production right now, so I don't want to mislead and say it's 80 out of the 250 on the planet. That's not correct. We have over 10%, if we use that number, we have over 10% working quantum computers today. And I'll talk a little bit more about that. So just, we know it's still at the beginning of this, at the forefront of this, and I think that number gives you an idea. So I want to talk a little bit about IBM Quantum. Of course, I work for IBM and in the quantum group, and we do two things. We're trying to bring useful quantum computing. It's all about solving problem with technology that happens to be quantum, but we also protect the three guys that were just up here, the CISOs in the room, anybody who has responsibility for security. This is an important piece. I'm going to talk about it at the end. It's not my expertise at all. I'm on the quantum computing side. I'm certainly not an expert in quantum computing either, but there's if it's for me, tell them I'm busy. So we've got, I'm on the quantum computing piece, but I want to touch on this because current cryptography will break in the next X number of years because a quantum computer will be able to break it. And I'll show you why, and I'll show you how, and I'll kind of back up that statement a bit. But we should be concerned about this. In fact, the bad actors today are doing something that we call harvest now, decrypt later. It's like stealing a box that you have no idea how to break into that box, but you think you'll be able to break into that box in a few years. So it's called harvest now, decrypt later. It's something we all need to be aware of, and it is coming. So there's cryptography, that current cryptography will be broken with, as if we didn't have enough things to worry about, with quantum computing in the future. I'll talk just a little bit at the end about that. Yes? Absolutely. So NIST, thank you, National Institute of Standards and Technology has come up with three or four quantum safe, what we refer to as quantum safe encryption. So if you think of RSA as being the former encryption type, there's three to four different new types of encryption that are quantum safe. Exactly. 3 of those 4 were designed by IBMers and submitted to NIST by IBM. So we very much are on the side of protecting against the threat of it. But thanks for the clarity there, because yeah, it's not that we don't have a path to be protected, it's that we need to get on that path. Yeah, thank you. Cryptography background, or? All right, so you'll join me up here because it's not my space when we get to quantum safe. This is what we're trying to help clients do today. We're trying to help them from just being quantum aware. Part of my job as an ambassador, as a quantum ambassador, you have to go through a kind of a quite formal program internally with an IBM to do that, is to talk about it, to make you all aware of what is this quantum computing stuff and what might be possible. But it's actually to accelerate them. And so we have a number of ways we engage with clients, that we paid for engagements where you hire our quantum consultants, a very different group than the typical IBM consulting team. It's the research scientists that are involved in that, and you get access to our computers, and we accelerate your adoption of quantum computing. And to the point that in the next several years, when people are putting things in production, that you'll be ready for that, and you start to get on the path now. So we are all in on these 3 areas: hardware, software, and our expertise. And so I'll just touch on a few things here just to make you aware a little bit more of what quantum computing is, what we're doing with it, et cetera. We're almost at 10 years now that we've had a quantum computer on the web, on the cloud. So you could, almost 10 years ago, 2016, you could get access to, at the time, a small, not physically, but powerfully, a small number of qubits in a system online that you could actually run a quantum computing job in 2016. When we speak or attend conferences, especially at universities, the college kids thank us for this, because they can do it for free, a little bit of time for free, and they can use the open source software to actually go do something with the quantum computer. And so it's a starting point for them. In 2016, we did that. Our official software, open source software, came out, Qiskit, in 2017. Currently it's used by about 72% of anybody that's doing anything with quantum is using our IBM Qiskit software. And so even the different hardware, there are other hardware vendors out there, they're still using our software. 2019, that's which picture of the System 1. That's the one that went to that's the model number that went to Cleveland Clinic. And that was our first official commercially available quantum computer. And then since then, we've introduced the, here we go. That's what it looks like on the inside of the System 1. We call it a chandelier. It's kind of an expensive chandelier, but it's actually a cryostat. So at the bottom of that is to have atoms behave well. They have to we get that down to about 15 millikelvin at the very, very bottom. So this is the pieces of that are the cryostat to actually cool this system. So that chip, it's down to 15 millikelvin. That's about 470 degrees below Fahrenheit. It's really cold. And so that's because we need to shield those chips, the qubits, and keep them cold. So each stage of that is getting colder as you cool that with helium, and it also, we send signals to that. So there's a classic signal that goes down to the qubit, manipulates it with a microwave pulse, and that's how we do part of the computation. So that's on the inside of that little tower that you see here. And then we introduced the System 2 a couple years ago. I'll show a little bit bigger picture of that, I think, on the next screen. So that's the System 2. I'll give you a perspective on that in just a minute. That's up in our Think Lab in Yorktown in our research center. And that's what's inside of it. So now we have these 3 cryostats, or 3 chandeliers, in there with three of the chips on the bottom. So you can see the scale of where we're headed with this, and up to roughly 500-ish qubits on that particular system. We're kind of changing them all the time, and they're updating. So one of the measures of how powerful a quantum computer is the number of qubits, but it's an imperfect measurement if you're trying to compare quantum computers to quantum computers, because there's other things, how we actually connect the qubits and other things to assess those. But that's the inside, and then that's actual size. So now you know how tall I am, and I'm not very, but that's the system, me standing next to the system too, just to give you an idea of the scale of the system. Now, we're certainly not going to go through the details of this, but I wanted to show you something. We've been publishing our quantum roadmap, and we publish it out pretty far, out to 10 years or so. We've been doing this, and now it's funny to kind of watch the competitors are now publishing their roadmaps as well, but we've been doing it for about 7 or 8 years because we want to tell you what we're going to be doing so that you can be planning for that. And some significant things then, again, this is published, you can actually get access to it on on the quantum section of our website, but so it's public, but I want to highlight just a couple things that are significant in the quantum world. Next year, 2026, we have said we will show quantum advantage. And our very conservative leader, Jay Gambetta, has said this. So it's going to happen. I have 100% confidence it's going to happen, where we show quantum advantage. What does that mean? It means there's absolutely no question. It's provable that what we did over here in quantum was better, faster, cheaper than what anybody can do with classical. It's significant. And there's been even arguments about how do you define quantum advantage. So we wrote a paper, an 8-page paper, defining how what quantum advantage actually looks like. But it's significant. 2026, next year, we will show that. It will likely be related to quantum chemistry, something related to quantum chemistry, most likely. The other one that's significant is out in 2029. Our also very conservative leader has said we will have a fault-tolerant quantum computer by 2029. I don't assume you've been studying this for a while, but there's still a lot of faults with, just like classical computers. When we first started in classical, there were a lot of faults. You had to figure out how to do fault error correction, error mitigation, et cetera, and we're still in that stage. There's a name for it. They call it noisy intermediate something, NISQ. What's the S? But it basically, they're still noisy. They don't hold their coherence times very long because it's still formative. So it's significant for us to say we will deliver a fault-tolerant quantum computer in 2029. So these are some of the things to look for as you do that. And it's not just talk. We are literally building these systems now. That system 2. This is a system 2. This is just a created image, but that's the system 2 that you saw before. We are actually building a data center. We're pretty good at building data centers, or at least what goes in data centers, because we've been doing that for years with the mainframe and everything else. But we're doing that up in Poughkeepsie, which was lots of our data centers have been up there in the past. But in Poughkeepsie, I got to walk the room where they're basically bolting together, much more sophisticated than that, but system 2s together. But then you see here this is Blue Jay, and that's Starling. We have a bird theme in quantum. It's geeky stuff. But the Starling is the one that in 2029, and you get a little bit of an idea of the scale of how big that will be here compared to just one of the system 2s that I was standing in front of. So I was about that big there, and you get an idea just of the scale there. So we are building these. We have built over 80. We're building out the data center to house a bunch of system 2s, and we will get there. I'm very confident in that we're going to get there. Show advantage next year, and then we will deliver a fault tolerant in 2029. So I kind of highlighted these, a couple of the older statements that we made, and we proved out. We've checked off every single one of our kind of building credibility with the quantum community or the community at large. We've checked off every single thing we've said on our roadmap. We've checked off, and so that's a way to kind of build a little bit more trust as well with the community. We have lots of customers that are doing work with us. A lot of the research labs started with us, universities at first. But now it's transitioning into commercial accounts. You see some of them on the list here that we can talk about that are public, some we can't yet. But we have over over 300 entities that have done work with us, paid engagements with us, that are doing work, that are publishing papers. We have over, I think it's 3,000 papers that we've written with both our scientists and others across the globe. It won't matter what a quantum computing does, or that it's a qubit versus a bit, because you're going to interface it to go get something done. And so you're going to be the user on that end of it, and you're not necessarily going to know what piece of that was quantum and what was classical, which you shouldn't have to know necessarily. Now, there's massive interest in quantum computing now, so people want to know how does a transmon superconducting qubit actually work, which are the types of qubits that we use. A couple different ways to build qubits. You can build them with photons, you can build them with trapped ions, etc. We build them with superconducting qubits, superconductors. But again, we are building out, even our software now is to the point where we have a app store for quantum computing. It's not quite an app store, it's not available on your iPhone, but it is software developers are augmenting what we're doing with Qiskit to do deeper things in optimization or simulation, etc. A couple really strong ones that are doing some really cool work with us, and that's another good sign for all of us, is that these software developers are going deeper and doing more. I'll briefly touch on use cases, not to go too high level. You can take a picture of this if you want, but this is industry ideas, kind of ideas by industry, and kind of I actually have 4 areas here versus the 3 areas that we talked about earlier. But it gives you just a quick snapshot based on your industry of some of the areas and ideas of what you might be doing. I'll leave that up for a second there to respond, or to let you can take a photo of that if you'd like. So lots of industry touches. One of the ones that's been first has been finance. But it's simulating nature on the like the Boeings, the Lockheeds, the Bosch, a bunch of them, and simulating nature. But then on the optimization side, finance has been a big one. Almost all the key finance companies have programs right now or are exploring things. To quickly touch on a couple, I was with Bosch earlier this week at the ACS, American Chemical Society conference in DC. That's where I was just before this one. And Bosch talked there about how they're doing simulating materials, again, with our quantum capability and our team. Wells Fargo was an early adopter of this, doing anomaly detection and a variety of other things in finance. Moderna predicting mRNA structures, things I know very little bit about, but a lot of interest in the healthcare industry, especially like with Moderna. Cleveland Clinic was the first one to actually have a quantum computer outside the walls of IBM. E.ON is the first energy utility to actually go in on quantum computing. They've been a little bit slower adopter, but now really exploring that. Think of the Duke Energy, the equivalent of a Duke Energy here, or whoever the local energy company is here, that is the equivalent in Europe. And so they're doing some really interesting stuff there. Even things like fleet optimization. You think about if a hurricane comes through or a tornado comes through, if you start to think about the optimization problem of that, one thing we're working on with NASA is the impact of floods. And we can't stop a flood, right, with a quantum computer, I guess, unless you line them all up at the beach. But what we can do is get better prediction of where their impact is going to go. We've shown some good results in that initially. But then you can optimize the fleet for everybody getting out to respond to it afterwards. Or think the same thing for the power grid. If we know this tornado is coming through, we may be able to optimize the way that we deploy the fleet for that. In the defense industry, you could naturally gravitate toward wargaming and the optimization challenges and logistics challenges in defense. So I want to talk about just one specifically that we're working quite closely with, Hyundai. They tried to do an experiment with us on electric vehicle route optimization. So you can start to think about, okay, if they're starting to do this, then where else might these types of things be deployed? And you can kind of have that innovation, your ideas generation get going. But it's kind of complex because it's multivariant, and they were trying to minimum distance, minimum time, and number of trucks, but then they also have to layer in time to charge and things like that. So a lot of different variables in this optimization problem. Can we do it today with things like CPLEX and other classical tools we have? Yes, and it's currently better than quantum. But the promise of quantum, especially with multivariables, is very promising. So that as soon as you start adding in more variables, it becomes really, really hard with classical. And it won't be as hard in quantum as we get better at this, as we develop and refine the algorithms. So some good results with that. I promised I'd touch on quantum safe for just a little bit here, then we can open it up for questions and I can try to answer questions. But again, this is not my expertise. We have a whole team dedicated to this, what we call the quantum safe side. But I just want to touch on it so that people are aware of this, that the current day, and again, you're absolutely correct, we have some of the new encryption that's quantum safe today, but what we might have in our portfolio of encryption today looks something like that list that you see on the left there, and those will be broken in the future because of what's an algorithm it's a quantum algorithm called Shor's algorithm. It's based on factorization. If I go P times Q and have a really big number, that's kind of what encryption is based on. But if I want to go the other way, I can't. And that's why encryption works until quantum. And quantum now will be able to do factorization and go the opposite way, okay? So again, high level, but just want to make you aware that this is coming and it's, it's here already. So we talked about this, we call it Q day, this day when a quantum computer will be able to break existing encryption, Q day. But it's so the bad actors are harvesting now so they can hold that and unlock it at some future date. IBM is quite restrictive on who we allow to access. Certain countries are absolutely off the list for being able to access a quantum computer, as you would imagine. But bad actors are good at what they do. Unfortunately, very, very bright people applied to wrong intentions. And so there's kind of a roadmap of what they might be able to do, which is why NIST, National Institute of Standards and Technology, and others got ahead of this years ago, and we've been working on this problem for years now to come up with a solution for that, so that we are starting to embed things like embed quantum safe encryption in our big mainframe platform that has been going away for, 30 years now? People have said the mainframe is going away, right? And it still goes, and it still runs all these massive transactions across the globe. But those are the types of things. And in the blue up here, the crystals and dilithium and the Falcon, those 3 out of the 4 are some of the new quantum safe encryptions. So again, from a simple standpoint, if you had RSA before, you might have one of these crystal encryption methodologies going forward. So those are the 3 of the 4 that we were deeply involved in. We IBM research and our scientists involved in actually creating the new types of encryption so that they would be quantum safe. And we have a whole practice that does this. We have new products, because it's not just it's part of the challenge, frankly, is finding out where do we use encryption today across the business, because it's embedded in so many processes. And so that's part of what one of our teams does, is they help you to find out, okay, this is where you have encryption. Now, how might we replace it, and what do we need to replace it with? So again, wrapping up here, and then we'll open it up for questions that I'll try to answer. But I really do hope you had just a few insights today, maybe a little bit more understanding about what quantum computing is, what the potential might be. But the ideas are endless of how quantum will be applied. And that's why it's so much fun to be a part of this program. Just been in it a couple of years now, but it's so much fun to be a part of and associated with IBM, who's leading in this space and really will begin to solve new problems with our clients and really a growing ecosystem of companies to do that. So I think I had, the recommended actions on this is basically keep learning and get started is really the fundamental things. Is you've got to keep exploring this, read the books, talk to more people, engage with others, understand what customers are doing, come to some of our events, attend some of our webinars. Olivia Lanes, if you Google Olivia Lanes and quantum, you'll find a YouTube channel that's brilliant. She's a wonderful friend now, and she's just a wonderful human being, but she's done a ton of education, free education, Olivia Lanes. And if you just Google Olivia Lanes and quantum, you'll find her, and she's terrific. We've got a bunch of free courses and videos out there. Great. So the message is start now. And this is the only role I've had in a kind of a business development role where I could not promise an ROI. I can't. If anybody is coming in and saying, we'll deliver a ROI, return on investment with quantum, run, because it's not here yet. But I can promise it's coming. And that's what's so exciting, is there's tremendous potential here, different type of compute, solving new problems. And so very excited to kind of be a part of that. And I can field any questions then. Yes?
Compared to Google quantum computer, where is IBM? And did Google already announce quantum supremacy?
Yeah. The question was basically, how do you compare to Google? I'll translate it into how do you compare to Google? And they talked about quantum supremacy. And so they didn't use quantum advantage. Google's a formidable competitor. I have great admiration for Google. So don't read anything in this that I think Google's not a good company. They are. I've got close friends that work there. They are not, their quantum program is not as advanced as ours. Personal Duane opinion is Amazon, Microsoft, Google, they're ahead of those three, and we're ahead of Google. And I say that because we've been doing it longer, we have more systems, we have bigger systems, we have more engagement with customers, we have a bigger ecosystem of our customers, all those reasons. When they said quantum supremacy, they got a flurry of, no, it's not, and that kept coming to them. And then people were trying to prove it out classically. That's exactly what's gonna happen when anybody says, this is better than classical. And it should happen. And what's fun is actually to watch the fight. Because then all the classical guys, oh, I could do that. They start cranking away on their keyboards and they invent something different, or they try to solve it differently. So we would define, and this is kind of getting into semantics, but we would not define what they said as what we're going to deliver next year with quantum advantage, where there's absolutely positively no question that we are better than classical, and it can be proved, it can be shown. So they are a formidable competitor. I think they're kind of in the number 2 position, my opinion, not a broad opinion. Certainly one to watch, and we want to stay ahead of them. Yeah.
You speak to the intersection of quantum computing and AI, and which AI models would be most applicable to the move to a quantum?
Yeah, we don't have a complete answer to that question yet. Let me just comment a little bit on where we're at with quantum and AI right now, from what I know. I mean, there are deep scientists that can go much deeper than this answer, but we're just at the forefront of combining and leveraging and figuring this out from a quantum plus AI, AI plus quantum. Let me give you one example and then a little bit more information. Today, we talked about, Sam talked about our Watson X capability, and we have actually a code assist capability from IBM that can actually write code. It's AI-generated code that can help a programmer do better coding. We're applying our Watson Code Assist tool to write Qiskit software to write better algorithms for a quantum computer. So AI helping quantum. We also are combining like anomaly detection or fraud detection. That's an area that I think will be next in another wave that's coming, where we will see QML, quantum machine learning, did it better or with less data than classical did. So we're right at the forefront of this, and we don't have it all figured out by any means of trying to figure out exactly how is this gonna work, because big AI, classical AI requires big LLMs, massive amounts. We're not gonna replace that. But we might be able to do an algorithm that somehow leverages pieces of that to do like fraud detection and anomaly detection. So it's a partial answer, I think. Was there another?
Yes.
Oh,
Sorry.
Somebody's got the phone.
Yeah,
Or the
I'm
phone,
back here.
Okay.
Sorry.
Yeah.
Could quantum compute power enable AI algorithms to be more efficiently implemented and even cost effectively implemented because of the compute power?
The short answer is yes. Yes, that this is one of the applications that we'll be further exploring. And you saw that huge Oak Ridge National Lab supercomputer. It's an incredible, and you all know more about this than I do, about supercomputers, and some of the talks will be about this, but how much energy that takes, how much cooling it takes. And while our system is big, the amount of compute power you're gonna get out of that footprint is literally exponentially more powerful than the Oak Ridge National Labs Summit supercomputer we saw. So that's where it may apply. Thank you, thanks for the question.
another question.
And then we have got to have a hand over here then too.
You mentioned Shor's algorithm. My understanding is that algorithm is going to break the current encryption methods. And there is another algorithm called Grover's algorithm. So are these algorithms in production now in any applications?
So Shor's is factorization,
Correct.
Grover's is search.
Searching, yes.
And so where that applies, non-scientist version, is in optimization. And so, but it's not always just, it's optimizing search, but that can kind of be used for optimization problems because we're searching for the most effective route for that Hyundai electric vehicle to get from here to here to here
Correct.
to here. So it's Grover's algorithm that will be applied for search and in optimization.
Okay.
But what's interesting is we just established a National Quantum Algorithm Center, affectionately known as NCAC, National Quantum Algorithm Center in Chicago, where I'm from, and that is to explore these algorithms that haven't been invented yet. And so there's a whole new area, an arena of quantum development around new algorithms that'll be remarkable. I mean, when we look back 5 years from now, it's going to be, I think it's just going to be incredibly promising and incredible to watch. Now, was there a question over here? Yeah.
Hi, thank you for coming and speaking. How does quantum computing react to Moore's law of evolution, and are we going to see a rapid decrease in size and cost as the computing power escalates, or is it off the grid from a physics standpoint?
So super interesting question because Moore's law is almost what's driving us to a new type of compute. So because we can only pack those bits so close to each other. So Moore's law is when compute power would either double or basically either 12 or 18 months-ish, right? And we are going to kind of hit that, although there's always new inventions that come out and going to kind of hit that where we can't pack any more compute power on this particular chip, even though they're measured in 5 nanometers or something like that, or getting closer to 2 nanometers where we can put them next to each other. So if Moore's algorithm won't apply to, Moore's law, sorry. It's kind of a new paradigm to think about when you think about computing power because we're going to be able to, we won't face that size restriction for probably another 20 or 30 years in quantum based on the way qubits are built and put next to each other. That's kind of a partial answer, I think. I don't think I completely answered your question. Okay. Yeah. All right. Yep.
So what sort of energy requirements to run this? If you can talk about the latest one you have been building, especially in terms of cooling.
Yeah. The cooling it's interesting because the cooling is done with helium. And I think we use 2 different isotopes of helium and actually blend them. And when I talk to the scientists, we call them lab rats, but when I talk to the scientists, they say, the cooling is not the issue. This cryostat is really an engineering feat that we've already solved. So that's not, so they say it's not that hard, that piece of the cryostat of actually cooling it down to that level. And most likely, there may be discoveries at the qubit level that cause it to be a little bit warmer, potentially. That's another potential. But when you compare, which is really hard to do exactly, but when you compare the compute power of a quantum computer compared to a classical computer, we're going to be able to do so much more in that smaller footprint. So this is a partial answer to building out more and more and more data centers because it will be able to be a smaller footprint using less power per computation in the future. But again, not all here yet. But what I actually am working with some utilities here in the United States, and the CIOs always ask me, do I need to prepare for this for all the data centers, quantum data centers I'm going to have in my territory, and the answer for the short term, next 5 or plus years, is no. because I answered that by saying there's only 250 quantum computers on the planet right now. So it's not an imminent problem from a power consumption and building out massive data centers. So partial answer again there. Okay, yes, over here.
Are there specific problems that a quantum computer can't solve that only classical computing can approach?
Yes, but I don't think we've ever kind of looked at it from that standpoint. But the answer is yes, because it's not good. Like for example, it's not good at building an LLM. It doesn't do well with big data. Okay, so that's not something quantum is good at. Finding something in that big data is but not dealing with big data. So it's and this will be clearer over the next 2 years or so of exactly quantum is really good at this and not good at this, and that'll continue to be developed. But as you think about the simulating nature at an atomic level, really hard, complex optimization problems, and then QML, those three are the ones that it'll be good at, but not big data stuff, other big data stuff. Again, okay. We have time for maybe one more question or so. Okay. Anything else? One more. And thank you. Appreciate the questions. And again, I have much smarter people behind me the team that literally almost everybody I work with has a PhD in at least something, at least one PhD. So we've got many more, we can go much more deep technically. Yes, go ahead.
I appreciate you coming out. So like, as like a consumer grade products come out and it's like, a Dell laptop with quantum or something, like, as that happens, like, are you saying that you envision it always being paired with classical in some way? Or is there going to be a computer one day that's like, this is a quantum computer with exactly what it is? Just kind of curious. And do you have like, not holding you to it, but like a general time frame when you think there could be some kind of consumer grade quantum advertised, personal laptop or something?
Right now, we don't see a path toward a quantum computer in the home. I will quickly say that an IBMer in the 1960s said there is no market for computing in the home. So we've been wrong before. We also kind of gave up on operating, the PC. Yeah. But so we've been wrong before with certainty. We don't see a path toward that right now. And we see the path of accessing it in the cloud where you don't even know that you're running a quantum algorithm because it's all connected in the cloud and you're on your laptop, your classical laptop, and you're doing work, and it just happens that this particular job, just a bourbon profiling algorithm just ran so that you can say, you know what, I'm gonna really like this new bourbon, but I gotta wait 3 more years. I don't know what it is, but trying to tie some of the things we've talked about today. But so we don't see a path toward that. We've been remarkably wrong in the past, and we do see this for the next 10 years or so as being mostly cloud-based, and that most of those we saw. Thank you.
Wonderful. Thank you, Duane.